All right, in this set of slides, we'll review the basic geometries of VSEPR. Our lesson objectives will define the basic geometries predicted by VSEPR. We'll learn the bond angles predicted by the theory for basic electron geometries. We'll use assumptions of VSEPR to explain geometries and bond angles, and we will discuss when basic geometries apply. So when you have a steric number of 2, the largest angle that you can form between those domains is 180 degrees. The bond angle is 180 degrees, and this configuration is called linear. When you have 3 electron domains, the furthest apart that those 3 domains can be is 120 degrees. This configuration is called trigonal planar. Why? You have 3 different domains, trigonal, and planar. It's flat. It's in the same 3D plane. All 3 of these atoms are in the same 3D plane, so it's flat like a sheet of paper. Trigonal planar. Once you get to a steric number of 4, we must now spread out into 3 dimensions in order to get as much space as possible. For those of you that remember and excel at geometry, you can calculate the bond angle here to 109.5 degrees. If you would like to see this math, there is a link in the word tetrahedral to a video that goes through it step by step. It's about 8 minutes long. I digress. All of these bond angles are 109.5. They're all equivalent. Actually, it's 109.47, but we round. The tetrahedral shape is the most common one for you when you encounter it in organic chemistry. Why? Organic chemistry includes a lot of carbon, which tends to make 4 bonds, which will have a steric number of 4. You see where this is going. Obviously, if you have double bonds or triple bonds off the carbon, this changes the equation. But if everything's a single bond, you will have a tetrahedral arrangement. What about a steric number of 5? In this case, we end up using all 3 dimensions again, and we cannot possibly find a way to make all of the bond angles equivalent. This shape is called trigonal bipyramid. Again, tri meaning 3, so we have 3 points around the center, and pyramid, you can make a pyramid shape if you connect each one of the neighboring atoms. You have one pyramid stacked on the others, thus bipyramid, 2 of them. We're going to go to another slide to talk about these angles. So we have a 90-degree angle and we have a 120, but we don't currently have adequate vocabulary for explaining why we have a difference. There are 2 different bond angles in this shape, as previously stated. To properly distinguish between them, we'll introduce some new vocabulary. Axial positions, in red, are straight up and down, like going through the poles on a globe. So if the atoms are 180 degrees away from each other, it is in an axial position. Equatorial positions are at angles around the central atom, like they're going around the equator on the globe. Equator, equatorial. I hope that this analogy will help you remember. So let's go back to talking about bond angles. So there is a 90-degree angle between each axial position and each equatorial position. So I've represented them for the upper chlorine on this, and I've given them a green color and an arc with 1 line through it. All of those are equivalent. If we were to draw them from the bottom chlorine up to the equatorial position, same thing. If you look at going from equatorial to equatorial position, then those are 120-degree angles, and I've represented them with light blue, and they have 2 lines coming out of the angle. So in the end, you have more space for your domain if you're in an equatorial position than if you're in an axial position, just based off of bond angle alone. 120 is greater than 90. Okay, so now that we have this idea that we can have 2 different bond angles and it depends on the position that you're in, let's go on to our final steric number. We have a steric number of 6, and you get an octahedral shape. Why is this called octahedral? Octa meaning 8, but this doesn't look like 8. What in the world? What are you talking about? There's 6 things coming off of it. That's not act. What is that? If you draw lines from each outer atom to the next in all directions, you make an 8-sided figure. I did attempt to represent this, but my handwriting made an indecipherable mess. So please go ahead and try this for yourself if it would help you to remember that it's octahedral, but it makes 8 planes on this shape. All of the bond angles in an octahedral shape are equivalent at 90 degrees each. So when do these basic geometries apply? When all of the outer atoms are the same thing, when all of the domains are bonding domains, and when the bonding domains are all single bonds. If any of those three is not met, it will not exactly match the basic geometry. It will have different bond angles. So let's say they aren't all the same thing. Then the geometry will distort away from the most electronegative element, and the atom usually becomes asymmetrical. There are some examples where that's not the case, but generally, if you've got one thing that's not like the others, the most electronegative thing will push the other things away because it's more negative. All right, second case. Not all of the domains are bonding. So if we have a lone pair or an unpaired electron, generally speaking, lone pair domains are always going to be much, much larger than bonding domains, and so the bond angles are smaller than those in the base geometry. Why is that? A lone pair is not in a bond, so it cannot make a bond angle. It is taking up more space than a bonding domain, and so it pushes the bonding domains closer together. So the bonding domains have smaller angles than in the basic geometry when you have a lone pair. For unpaired electron domains, they're closer in size to the bonding domains, so it's a little bit difficult to predict the over-under on that one. I just usually use the squiggle. It's about that bond angle, and I call it a day. I don't give it a greater than, less than. I just say it's in the neighborhood of. Okay, finally, when you have greater than single bonds, we know from our book that the lone pair domain is the largest, the triple bond domain is the second largest, followed by double bond, followed by single bonds. So if you have a double bond domain, it is going to take up more space than a single bond domain, and the angles involved with those in the double bond are going to be larger. The ones with the single bonds are going to be smaller. So it just distorts the shape based off of how many electrons you have. To summarize, basic electron geometries are linear for a steric number of 2 with bond angles of 180, trigonal planar for a steric number of 3 with bond angles of 120, tetrahedral with a steric number of 4 with bond angles of 109.5, trigonal bipyramid with a steric number of 5, 2 different bond angles, 90 degrees for the axial to the center to the equatorial position, and 120 degrees for equatorial to central to equatorial. And finally, octahedral with a steric number of 6 and all bond angles equal to 90.